Hey class, we're starting chapter 13 this week. Last week we looked at gases, this week we're looking at liquids. So we're just going to review some of the properties of matter really quickly. We've seen that there's different forces that hold matter together in this class. The forces that hold all those subatomic particles together in atoms. Ionic compounds, those coulombic forces that drive opposite charges together. So the big force that we're going to look at, the forces that are between molecules that we're going to talk about in this chapter, are called intermolecular forces. During this chapter, if I ever refer to an IMF, or I write IMF down, I'm referring to the term intermolecular force, which you probably read about already in your text. I'm not going to go over that in a lot of detail. It's the forces that are between different molecules that hold them together. So remember all the way back to I think it was chapter 1, we talked about the forces of attraction between different particles in matter. We said the intermolecular forces are what determine the physical state of the compound. So just as a little mini review, we have the three physical states shown here in the following diagrams. Depending on what's depicted, we can actually determine which of the particles we're looking at. For example, I'm going to call this A, I'm going to call this B, I'm going to call this box C. So if you look at diagram A, we know that this represents the gaseous state of matter. So this represents gas particles. These are particles that are relatively far apart, they have random motion, they're independent, they interact independently of one another. This is what we talked about in chapter 12. They have little to no contact. The intermolecular forces are basically non-existent in these compounds, and therefore the motion is random. Alright, on the other side, C, we have solids. And remember, solids contain particles that are very closely packed in space. They maintain their rigid shape, whatever the shape of the container is, that's the shape they are. And they have significant attractive forces that exist between particles. They're in close contact, they have very high intermolecular forces, these IMFs are very high, and that's what helps them maintain their rigid shape. What we're going to be talking about in this chapter, and we're actually going to get to solids and gases as well, but we're going to start off by talking about liquids. So what have we learned about liquids so far? We've learned that liquids are intermediate between gases and solids. They contain particles that are close to one another, as shown here, but they have fluidity, which means they can assume the shape of a container. They can move around, slipping and sliding past one another. They flow when they're poured. There's significant attractive forces or intermolecular forces that exist between the particles, or else they wouldn't be in contact with one another. So, like a solid, they have relatively high intermolecular forces. That's what's keeping them close in contact. Not as high as the solid, but relatively higher than gas. So they have some attractive forces then, and they're fluid in their shape. So what we saw in those diagrams then were that the intermolecular forces that are felt between the particles in the various states counteract or are different, opposite, from the kinetic energies of the molecules keeping them apart. What this means is the higher the kinetic energy of the particle, the less the forces of attraction between the particles are felt between one another. The physical state of any matter, solid, liquid, or gas, as well as the intermolecular forces and the kinetic energy then, is dependent on the temperature of the sample. The temperature of the sample. So, when we're at higher temperatures for a particular substance, when we're at the high end of temperature for that substance, the particles typically have high kinetic energies overall, and higher kinetic energy means the intermolecular forces are more weakly felt. So when you're at high temperatures, you have high kinetic energies, low intermolecular forces felt between particles. that's how we defined, once again, the gas phase. When we're at moderate temperatures for the substance, and that can vary per substance, we're going to have moderate kinetic energy of particles and more strongly felt intermolecular forces than before because we are at lower temperatures. So this is when we have a liquid state. And then finally, when we're at the lower temperature end for a substance, we have low kinetic energies. And when the kinetic energy of the particles is lower, they're moving more slowly, the intermolecular forces between the particles is felt very strongly. And this is when we have conditions for a solid. So the interesting thing here is that the attractive forces, the intermolecular forces, for the particles, let's say you have water, the intermolecular forces that exist between water molecules never changes. It's actually the same in all phases. However, because of the increasing temperature, you have a higher moving or higher kinetic energy particles, and the higher the kinetic energy, the more temperature you have to overcome the forces that hold those particles together. So kinetic energy overcomes the innate forces of attraction between the particles. What we see most of the time then is that a substance, every substance has its own unique individual intermolecular force of attraction between those particles, but the intermolecular forces might be different from substance to substance. And as you increase or decrease the temperature, most substances can exist in all three states, solid, liquid, or gas. Like water. Water exists as ice in the solid state, liquid water, and then steam in the gaseous state. But not all substances, remember, exist in three phases. For example, carbon dioxide. Carbon dioxide, we know generally at room temperature, at standard temperature and pressure, right? It's a gas. We breathe it out right now. And if we cool down carbon dioxide to the point where the intermolecular forces are stronger than, more strongly felt than the kinetic energies of the particles, basically we've converted this gaseous carbon dioxide into solid carbon dioxide, which is known as dry ice. So carbon dioxide can exist in solid form, dry ice, and we know that that sublimes or is converted easily from the solid to the gaseous state by increasing temperature without going through the liquid phase. So the compound's known to sublime. So it never actually reaches the liquid phase, and that's just one example. Another example, sugar. You can't actually melt sugar. Sugar actually decomposes at high temperatures. So sugar is solid, and you can't have liquid or gas. It will decompose. Alright, so now let's move into talking more about liquids then. Of these three physical states of matter, let's talk more about the liquid. Alright, so here we have a depiction of a beaker that is closed. There's a glass lid on top, and inside of that beaker is, let's say, water, and so there's water molecules there. What we need to know about, the first thing we need to know about liquids is that liquids are never only in the liquid state. The head space above a liquid, shown here, okay, so here's your liquid. The head space above the liquid, if that were empty, is not always empty. It's filled with the gaseous phase of the matter. The gaseous phase of the matter. What happens is particles that are in the liquid phase those molecules tend to escape from the liquid phase into the gas phase above the liquid, the head space. So the liquid phase becomes into the gaseous phase. And by the way, there's a special name for the gas phase, or the particles that escape a liquid and become gaseous or separated far apart, not in close contact, in higher kinetic energies. The gaseous phase of a liquid above the liquid surface is called the vapor. Have you ever heard of that word? So this is the vapor that exists above the liquid phase. So we see this with every liquid that exists. There's particles inside of the liquid that have average kinetic energies. So, which means that some of the particles in this liquid phase are at higher kinetic energies and some of them are at lower kinetic energies. Remember, they're moving around, slipping and sliding randomly. So overall, they have an average kinetic energy, meaning that some move faster and some move slower. If one of the particles that has a higher kinetic energy gets to the top of the liquid phase and it's headed out, it has the ability to kind of pop out, kind of like popcorn out of like popping in a vessel. It has the ability to pop with that energy out of the liquid phase or to escape into the headspace above, and that's how it becomes the vapor. So the molecules in the liquid state with the higher kinetic energies can overcome the attractive forces that are holding those particles down. There are attractive forces between the particles in the container. They all want to pull this particle here in, but that particle has enough kinetic energy to overcome all of those intermolecular forces, and it escapes into the gas phase. The phase change that exists from the liquid layer to the gaseous layer is called evaporation. And if the evaporation occurs above a liquid, sometimes it's called vaporization. So that's exactly what we're going to define first. Alright, so the process of going from the liquid phase of matter to the vapor phase, also known as the gas of that substance above the headspace of the liquid, the process of going from liquid to gas is called evaporation. Notice the word vapors in the word evaporation. The opposite, going from the vapor phase back to the liquid phase, which can also occur. In the headspace, you've got all these particles in the vapor phase bouncing around with the liquid. If one of them happens to dive kind of like back into the liquid phase, then it will be submerged again in close contact around other like molecules. That would be going from the gas to the liquid phase of matter. That phase change is called condensation. It has the word dense in it, condensation, because the particles are becoming more densely packed from the vapor to the liquid phase. So we have evaporation, liquid to gas change, and the vapor can return back to the liquid phase. That's called condensation. It turns out that if you're in a closed container, if you have a liquid inside of a closed container, it means it's capped, there's headspace above it, an equilibrium will develop. An equilibrium is a back and forth type of movement. So an equilibrium will develop where there are just as many molecules evaporating as there are condensing. Now what does that mean? If you've got just as many molecules evaporating as condensing, well, let's just kind of do a simple math experiment here, okay? So let's say I have 3 particles above the liquid. And let's say I've got lots of particles below the liquid. Let's just come up with a small number to make life easy. Let's say I have 3 particles above the liquid in the vapor phase. And let's just say, to keep things simple, I have 20 in the liquid phase. According to this definition of an equilibrium, it's a development where as many molecules are changing in one direction as they are in the other direction. Meaning, I have, for every liquid molecule that evaporates, I have one that condenses. So let's say that this molecule right here, one of my 20 in the liquid phase, vaporizes or becomes evaporated, part of the gas phase, and by equal exchange, if one molecule is evaporated, one of the molecules from the gaseous phase is condensed. So going from gas to liquid, vapor to liquid. Overall, is there a net change, if this is occurring in equilibrium, is there a net change in the number of gas particles and the number of liquid particles? In an equilibrium, no. It doesn't mean the amount's equal. Notice here we have 3 in the gas phase and 20 in the liquid, just as a random example. The gas phase particles, the number of them, are not the same as the liquid. However, the numbers remain constant. For every one exchange in one direction, there's an exchange of 1 in the other direction. So I maintain my 3 and my 20. This is called an equilibrium. You've probably experienced equilibriums before. If you've ever purchased like a bottle of water, you probably bought a bottle of water in a store. Okay, there's my little bottle of water. And there's the water at the top. If you kept that water bottle capped, let's say that you have it in your hurricane supply kit, I don't know, and you keep that bottle of water capped for a year. If you marked on that bottle exactly where that water filled, the fill line of the water in the bottle was when you first bought it, you come back a year from now, the fill line would not change. The amount of water or liquid phase in the bottle does not change. However, there's an equilibrium going on in that bottle. Notice all of your water bottles or other types of drink bottles have the head space above the liquid. That head space above the liquid contains the vapor of the water. As the water is heated and cooled down over the cycle of however long you have it, the particles in the liquid phase are converting to the headspace in the gas phase. But for every conversion that's in evaporation, there's a condensation occurring. So there's an equilibrium in the bottle. So overall, you see no net change in the amount of liquid particles in the bottle, even though they're constantly being evaporated and condensed. This is an equilibrium that's occurring, and there is vapor above the liquid. Alright, so now we're going to talk about what it means to have a vapor pressure. You've probably heard of vapor pressure before. Now, we just studied pressure of gases in Chapter 12. So we know that all gases exert pressure. It's the force per unit area that's put on the sidewalls of a container or any type of collision where the gas is going to collide with something. It turns out the vapor pressure is the pressure exerted by a vapor in equilibrium with its liquid. So what does it mean to be in equilibrium? Well, if you have an open, I'm going to blow this up, you probably can't see it. Let me blow it up on my screen here. Alright, so what does it mean for vapor pressure? To be a pressure exerted by a vapor, the gas of the liquid, in equilibrium with its liquid. What does it mean to be in equilibrium? So, I'll give an example here. If you take an Erlenmeyer flask such as this, and you put some water in it, and you leave that flask open, if you put the water in the flask and walk away for, let's say, 2 weeks, if you come back, what are you going to see different about that container? You're going to see that the water has evaporated, right? Over time, there is an exchange where the liquid becomes gas and the gas becomes liquid. But because that container is open, the molecules from the liquid phase that are vaporized into the gas phase have the ability to leave the container and enter the environment. It's not a closed system. So you're going to see that the amount of liquid will go down. However, if you take that Erlenmeyer flask and on the first day you fill it with water and you cap it, what's going to happen is initially there's none of the liquid water above the head space of the liquid. So what happens is the particles in the liquid phase have to begin to migrate into the gas phase. So originally the higher kinetic energy particles are going to start escaping from the surface of the liquid, and they're going to be vaporized into the gas phase. So we're going to see a net push from the liquid phase into the gas phase. It's not going to be an equilibrium yet, because a lot of the liquid will be first moving into the gas phase. However, over time an equilibrium will develop, because once this headspace gets saturated with enough of the vapor particles in the gas phase, you're going to see an opposite trend occurring, where now the gas phase is flooded with high energy particles and they will enter the liquid phase. And at the same time, what's the liquid doing? High energy particles. So over time, what happens is an equilibrium will develop into that container where the head space will fill with a certain concentration of the vapor of that liquid inside of it, and the rate of evaporation will equal the rate of condensation. And at that instance, an equilibrium is developed and maintained. The particles going from one to the other and the other to one, they will be equal in their rates. So when equilibrium is developed, if you measure the pressure of that vapor inside of that closed container, you get the vapor pressure of the liquid. So to recap, if you fill a container up, if the container is open, the process of evaporation will just continue until all of the molecules escape. However, if the container is closed when you fill that container, the molecules that escape will remain in the headspace above the liquid, and eventually an equilibrium will develop where particles are evaporating at the same rate they're condensing. The partial pressure of the vapor in the equilibrium with its liquid is called the vapor pressure of the liquid, and that's something that can be measured in a closed container. Vapor pressure, it turns out, and we'll need to know this, it's the next thing we're going to talk about, is a function of temperature. Vapor pressure is a function of temperature. That means that, or how it is so, is that if you increase the temperature of the liquid, remember what the temperature is. It's it measures kind of the average kinetic energy of the particles. So if you increase the temperature of the particles, you're saying that you've increased the kinetic energy of the particles of that liquid on average. And if you increase the kinetic energy of the liquid, you increase the kinetic energy of those particles that have escaped into the vapor phase. If they are at a higher temperature or a higher kinetic energy, then that means that their pressure is also higher. So at higher temperatures, we get higher vapor pressures of our gases, or the vapor above the liquid. So vapor pressure will increase with an increase in temperature. Now, does it increase forever? The answer is no. Vapor pressure increases with the temperature until it equals atmospheric pressure. Remember what we said atmospheric pressure was? It's the pressure of the atmospheric gases pressing down on the surface of the earth, or in the atmosphere. Why in the world would the vapor pressure increase until it equals atmospheric pressure of a liquid when it's heated, and it would not get any higher? It's because at the point when the atmospheric pressure equals the vapor pressure of the liquid, this is when the liquid boils. See, the atmosphere is what's holding the particles down, or pushing down on the particles to keep them in their liquid state. Once the particles have enough pressure or kinetic energy to not be held down by that atmospheric pressure anymore, they're no longer confined to the liquid state. They can boil or become in equilibrium with the gas phase. So we need to define what a boiling point is real quick. A boiling point is the temperature at which the vapor pressure of a liquid equals the atmospheric pressure. When the vapor pressure of a liquid equals the atmospheric pressure, that's when that liquid will boil. Normally, when we talk about boiling points, we're talking about normal boiling points of liquids. For example, if I tell you the boiling point of water is 100 degrees Celsius, technically I'm giving you the normal boiling point of water, which is defined as the boiling point at which the atmospheric pressure is at 1 atm. We said that was the standard pressure, right? So whenever the atmospheric pressure is 1 atm, which we assume it always is at sea level, that's the boiling point we usually report. The next thing to mention is that for liquids that are at the same temperature, the vapor pressure will depend on the strength of the intermolecular forces between the molecules in the liquid state. Have you ever wondered why something like a gas, like methane, for instance. Methane is CH4, okay? It's a gas that we use, like in the lab. We use methane gas for our Bunsen burners. Why does that have a certain boiling point below room temperature? So it's a gas at room temperature. And then water which is boiling point is way above room temperature, 100 degrees Celsius, is a liquid at room temperature. The reason why is because when these particles, let's say they're both at room temperature, 25 degrees Celsius. When both of these particles are at 25 degrees Celsius, water is a liquid because water has higher intermolecular forces that hold these particles together. Methane has lower intermolecular forces of attraction, so it's not held together as tightly. So at lower temperatures, it can overcome its intermolecular forces, and it's in the gas phase. So we're going to learn about these intermolecular forces in this chapter, what they are, and how to predict which will have higher intermolecular forces versus others. It has to do with polarity and charges. But we'll be talking about that. Alright, the other thing I wanted to talk about is what it means to be volatile. Have you ever heard of something being very volatile? Like fingernail polish remover. Someone might say that's a very volatile liquid. That's a term we want to know. The word volatile, used for liquids, describes liquids that have very weak or very low intermolecular forces of attraction between them, which means they evaporate readily. They evaporate at room temperature very easily. For example, if I spill fingernail polish remover on the counter, basically that's acetone, or it used to be anyway, versus spilling water. Water has higher intermolecular forces of attraction that hold those particles together. So water will not evaporate at room temperature very easily. So a water puddle takes forever to dry up versus something like acetone. Acetone has very low intermolecular forces between the particles. Low intermolecular forces mean you evaporate easily at room temperature because you're not held together very strongly, so you can evaporate easily. So, volatile liquids, if they have low intermolecular forces, what does this say about their vapor pressures? If you have low intermolecular forces, that means your liquid particles are not held together tightly. So that means those particles can escape easily into the vapor phase. So if you have lots of particles in the vapor phase at room temperature, it means on average you have a higher vapor pressure. A higher vapor pressure. Particles that have low intermolecular forces, substances that have low intermolecular forces between them typically have higher vapor pressures. Because many of those particles escape into the vapor phase. Alright, so let's try to see if we can wrap our heads around these concepts of volatile liquids, high vapor pressures, low intermolecular forces, vapor pressure versus temperature. So here's a few example problems. The first one says here, the vapor pressure of diethyl ether is 318 millimeters of mercury. So we're given the vapor pressure of diethyl ether, 300 millimeters of mercury. 318, I'm sorry. It says the vapor pressure of a different substance, the vapor pressure of ethyl alcohol, was 44 millimeters per mercury. So we have diethyl ether is 318 millimeters of mercury is the vapor pressure. And then we have, ethyl alcohol with 44 millimeters of mercury as its vapor pressure. It says, which substance has a stronger attractive forces between molecules? Alright, we're going to assume that these are measured at the same temperature. So at room temperature, we'll say, or we could say standard temperature and pressure, or atmospherically. What are the differences here in the vapor pressures? Well, diethyl ether has a higher vapor pressure, and ethyl alcohol has a lower vapor pressure. Let's think about what this means in terms of the intermolecular forces. If you're diethyl ether and you have a higher vapor pressure, that means that you have more particles in the gas phase at that temperature or at higher kinetic energies. Basically, it means you have more escapees. The higher the vapor pressure of the substance, the more escapees of the liquid into the gaseous phase. Now, why would you have more gas particles above the liquid? You'd have more vapor creating that vapor pressure because the intermolecular forces between the particles were relatively weaker. So, diethyl ether has a high vapor pressure because the intermolecular forces in the liquid phase holding the particles together is relatively weaker, so you have more particles escaping overall. Likewise, ethyl alcohol has a lower vapor pressure, which means there's less escapees from the liquid into the gas phase. There's less particles that escape into the vapor phase because there's generally higher intermolecular forces for lower vapor pressure. The particles in the liquid phase of ethyl alcohol are held together much more tightly, and they have less chance of escaping into the vapor above them. So overall, who has the stronger attractive forces? The lower the vapor pressure, the higher the intermolecular forces. All right, so it's ethyl alcohol. Ethyl alcohol. Yay, ethyl alcohol. All right, let's look at the next one. I'm going to erase what I wrote here so we can read it. Okay, it says in a system at equilibrium between the liquid and gas phases. So we have liquid, gas, or the vapor above the liquid. So we're in equilibrium. By the way, these are equilibrium arrows. They basically mean the rate at which the liquid's converting to the gas and the gas converting to the liquid is the same. So there's no net change in the concentration of the liquid and the gas phases. So that's what it means to be in equilibrium. So a system is in equilibrium between the liquid and gas phases. Which of these is true if they're at equilibrium? A, the particles stop changing phases. Is that what this arrow means? That the particles stop changing phases? I think if the particles stopped changing phases, we would put an X through that arrow, wouldn't we? No, that's not true. A is not correct. Particles maintain in equilibrium. The phase changes. The phase changes just occur at equal rates, so you don't notice a net difference. So A is not correct. Let's read the second one. It says B. The rate at which the particles change from liquid to gas exceeds the rate at which they're converted from gas to liquid. Does the rate in one direction exceed the rate of the other direction? No. At equilibrium, it means that the rates of exchange are equal. So B is not correct either, because exceeds is not correct. Let's read C. Hopefully it's correct. It says the rate at which particles change from the gas to the liquid state equals the rate at which they change from the liquid to gas state. This is true. Now, there may be more liquid than gas or gas than liquid, but the rate at which they are exchanging at equilibrium is the same. So C is the answer. That's what it means to be in equilibrium. All right, let's look at the next question here. The next question says, which has the lowest vapor pressure? So we want to look at low vapor pressures. All right. We learned, before I even look at this problem, we learned that vapor pressure is dependent on a few things. If a compound has higher intermolecular forces of attraction, that liquid will typically have lower vapor pressures. The other thing we learned that was dependent on vapor pressure was temperature. If you're at a lower temperature for a substance, you typically have lower vapor pressures. Okay, so let's read the question. It says, which is the lowest vapor pressure? We're given quantities of gasoline, so 125, 50, and 25 mils of gasoline. So we have the same substance in all of these. So we're given the volumes of the liquids. We're given what the liquid is, the substance, and we're given what else here? We're given the temperature of the substance. All right. Does vapor pressure depend on the volume of the substance? How much of the substance you have? The answer is going to be no. We didn't directly talk about this because volume has nothing to do with vapor pressure. But if you go back to what vapor pressure means, it's the pressure force per unit area of the vapor pushing back down on the liquid phase during that equilibrium. It's the force per unit area. That's what pressure is. So if you have more gasoline per unit area, the vapor pressure is still going to be the same as if you have less gasoline, because it's the per unit area of the force that counts. So basically, what am I telling you? I'm telling you that the volume of the substance does not matter at all. So that's just put there as a distractor to distract you. Alright, let's look at the substance itself. All of the substances are the same. So we're given different temperatures. Well, we did learn that vapor pressure and temperature are correlated. If you're at a lower temperature, then you're going to have a lower vapor pressure, because there's less particles that can escape, and they escape at a lower kinetic energy, so the pressure of the vapor will be less. So we find that the lowest temperature is A. So because we have the lowest temperature in A, 15 degrees Celsius, we should have the lowest vapor pressure. Alright, and now in this last problem here, we haven't actually talked about this exactly yet. We've talked about the trend. But what I want to do is, through this example, teach you how to read something called the vapor pressure versus temperature diagram. It's also called the vapor pressure curve. So remember that I told you, as you increase the temperature of a liquid, you increase its vapor pressure. We just mentioned that above. Or if you decrease one, you decrease the other. Vapor pressure is temperature dependent for a liquid. So if you take a liquid such as water, here's an example of water below. If you're at different temperatures of the liquid water, the vapor pressure of the water will be different depending on what temperature you measure it at. So vapor pressure is temperature dependent. So on this curve, we have two axes on this plot. We have vapor pressure, which I can't seem to write, and we have temperature on the x-axis. And the temperature is degrees Celsius. Alright, the vapor pressure is in millimeters of mercury, by the way. I know it's hard to read here. So what do we see as the general trend here? Now, it's not a linear curve, but as we increase temperature, as you go to the right, what happens to this line? Does it go down, or does this line go up? Well, we see that it goes up. Basically, what I'm showing you is this trend right here. As you increase the temperature from negative 10 degrees Celsius to 110, as you increase the temperature this way, you increase the vapor pressure of the liquid. So we see that the curve goes up, right? The curve is going up as it goes right. So this is the trend that we were talking about before. Now, when you read this curve, if you're given the temperature of water, you can find its vapor pressure very easily. This actually comes in quite handy for chemists. We use vapor pressure curves a lot when we're doing things like distillation processes of liquids or evaporations. So it says, what is the boiling point of water at 300 millimeters of mercury? Alright, now let's think about what 300 millimeters of mercury is real quick. Standard temperature and pressure we learned about in the last chapter. So what's the standard pressure at which we would boil water? The standard pressure at which we would boil water in the atmosphere is 760 millimeters of mercury, or 1 atmosphere, right? And we know that water boils at about 100 degrees Celsius at that pressure. What if we reduce the pressure of the system? We put it under vacuum conditions. That's basically what we're doing here. Instead of 760 millimeters of mercury, we say let's put the liquid inside of a vacuum and lower the pressure down to 300 millimeters of mercury. What will the boiling point of the water be? Well, first of all, I'm going to tell you the trend. Because if we're at a lower pressure atmospherically, remember the boiling point of water is when the vapor pressure equals the atmospheric pressure. You get the boiling point of water. So if you lower the atmospheric pressure, you lower the vapor pressure of the water. So I'm just trying to get you to think about this. So what should the temperature be if you're at a lower vapor pressure for boiling? If you're at a lower vapor pressure for boiling because you're at a lower atmospheric pressure, then you should be at a lower temperature. The water will boil at a lower temperature. Okay, so let's go to our little curve here. And this is not going to be exact because I don't have a ruler or anything. But at 760 millimeters of mercury, let's kind of draw that out here. It looks like the boiling point of water is 100 degrees Celsius. Ta-da! I just find the X and Y points from that point on the line. Alright, so I get my coordinates there, and I say at 760 millimeters of mercury, this is standard temperature and pressure, by the way, the boiling point of water is 100 degrees Celsius. So I say, okay, put this in a vacuum, get the atmospheric pressure down to 300 millimeters of mercury. Let's find that. So here's 300, and you come across, and at 300 millimeters of mercury, here's your point on that line, your vapor pressure curve for water. We're going to come down, and it looks about, I don't know, like 77 degrees Celsius. The water boils at a lower temperature. So that's the temperature at which water will boil at 300 millimeters of mercury. It's a lower temperature. This can be quite convenient and quite quicker for a chemist to boil at lower pressure versus higher pressure. So that's a vapor pressure curve, and it's very easy to read, and that's how we read it.